Hello and welcome to The Explainer. Today, we are diving deep into one of the absolute cornerstones of chemistry, chemical reactions and equations.
Yep, we're tackling Chapter 1 from the Class 10 NCERT science textbook. And listen, whether you're gearing up for your board exams or you have your sights set on competitive exams like the UPSC, this chapter is non-negotiable. Getting these concepts down is absolutely crucial. So let's get right into it. So here's our game plan. First, we'll figure out what a chemical reaction even is. Then, we'll learn how to speak the language of chemistry by writing equations. After that, we'll explore the different types of reactions, unpack oxidation and reduction, and finally, tie it all back to things you see in your daily life.
All right, let's kick things off with the big question. What in the world is a chemical reaction? The cool thing is, you already see them happening all the time, probably without even thinking about it.
Just think about it for a second. Milk going sour, that old iron nail in the garden getting rusty, even just cooking food. In all these cases, the stuff you started with is changing into something completely new. These are all chemical reactions in action. But the real question is, how can we be scientifically sure that a reaction has taken place? What are the clues?
Well, luckily, there are some really clear signs to look for. There are 4 key indicators. First, a change in state, like a solid turning into a liquid. Second, a change in color. Third, the evolution of a gas. You might see fizzing or bubbles. And fourth, a change in temperature. Maybe the test tube gets hot, or maybe it gets surprisingly cold. Now, here's a big exam tip. You are definitely going to want to remember these 4 signs.
Seeing a reaction is one thing, but as scientists, we need a way to describe it accurately and efficiently. And that, my friends, is where chemical equations come in. Think of it as the official language of chemistry.
So, we could say something like magnesium plus oxygen gives you magnesium oxide. That's a word equation. It works, but it's kind of clunky, right? Chemists prefer a shortcut, a much cleaner way to say the same thing, and that's the chemical equation. It's concise, it's universal, and it's packed with a ton of information.
But hold on, we can't just throw the symbols down. The equation has to be balanced. This is all because of a super important rule in nature called the law of conservation of mass. It basically says you can't create or destroy atoms in a chemical reaction. They just get rearranged. So the number of atoms of each element you start with on the left has to be the exact same as the number you end with on the right.
So how do we actually do it? Well, we use something called the hit and trial method, which sounds complicated, but it's really just a step-by-step puzzle. You draw boxes around the formulas so you don't mess with them, count up your atoms on both sides, find the messiest looking compound and start there, and then use numbers out front, called coefficients, to make everything match up. Then you just do a final check. Let's try one.
Okay, check this out. Iron reacting with steam. On the left, we start with 1 iron atom, but on the right, we have 3. Easy fix. We just put a big 3 in front of the Fe. Now look at the oxygen. We have 4 on the right side, so we need a 4 in front of the H2O on the left. But wait, that gives us 8 hydrogens on the left. No problem. We just need to put a 4 in front of the H2 on the right, and boom, everything's balanced. It's just a little bit of back and forth until it all clicks.
Awesome. Now that we know how to write the language of chemistry, let's look at some of the common story types, or the fundamental patterns of reactions. Knowing these categories is a huge advantage for your exams.
Let's start with 2 reactions that are basically polar opposites. First, you have a combination reaction. That's where 2 or more simple things combine to form one single more complex thing. A plus B makes AB. The exact opposite is a decomposition reaction. Here, one big compound breaks down into smaller, simpler pieces. So, AB breaks apart into A and B. Simple as that. Now, with decomposition, you always need to add energy to break those bonds apart. And we can actually classify these reactions based on what kind of energy you're using. If you use heat, it's called thermal decomposition. If you use electricity, like when you split water into hydrogen and oxygen, it's called electrolytic decomposition. And if you use light, it's photolytic decomposition.
Next up, we have the displacement reaction. I like to think of this one as a chemical swap. You have a more reactive element that comes along and basically kicks a less reactive element out of its spot in a compound. The classic example is when you drop an iron nail into a copper sulfate solution. The iron is more reactive, so it boots the copper out, and you end up with iron sulfate and plain old copper. So if one element can do a swap, why not 2? That's what happens in a double displacement reaction.
You have two compounds, and they literally trade partners, swapping their ions to form two brand new compounds. Now, a really common thing that happens here is that one of the new products is a solid that won't dissolve. We call this a precipitate. And when that happens, you can also call the whole thing a precipitation reaction.
Okay, let's shift gears to a concept that is, well, it's everywhere in chemistry: oxidation and reduction. For now, we're going to think about it in terms of oxygen and hydrogen.
The definitions are actually pretty straightforward. Oxidation is when a substance gains oxygen or loses hydrogen. And reduction? Well, it's the exact opposite. It's when a substance loses oxygen or gains hydrogen. See? They're two sides of the very same coin.
And here's the most important rule. They always happen together. You can't have oxidation without reduction, and vice versa. It's a package deal, and we call it a redox reaction. Look at this example. The copper oxide, CuO, loses its oxygen to become just copper. That's reduction. And where does that oxygen go? The hydrogen, H2, gains it to become water. That's oxidation. It's a perfect transfer.
So, we've gone through all this theory. But what's the point? Well, this isn't just something that happens in a lab. These exact reactions are going on all around you, every single day. Let's make the connection.
We just talked about oxidation, right? Well, two of the most famous and kind of annoying effects of oxidation are corrosion and rancidity. Corrosion is just the breakdown of metals. Think about iron rusting or silver getting that black tarnish on it. And rancidity? That's when the fats and oils in your food go bad because of oxidation, giving them that awful smell and taste.
This leads to a pretty cool real-world question. You ever open a bag of chips and feel like it's half full of air? Well, it's not actually air, and there's a very clever chemical reason for what's really in there.
And the answer is to stop rancidity. Chip bags are flushed with nitrogen gas. So why nitrogen? Well, we know it's the oxygen that makes the fats in the chips go bad. Nitrogen, on the other hand, is super unreactive. So the manufacturers pump in the nitrogen to push all the oxygen out. No oxygen, no oxidation, and your chips stay fresh and crispy for way longer. Pretty smart, right?
And there you have it. We've journeyed from noticing everyday changes all the way to understanding the language and patterns behind them. You now have the tools to look at the world a little differently. The next time you see a rusty fence or cook an egg, you'll actually understand the chemistry happening. So my question for you is, now that you know the science, what's one thing in your daily life that you'll never look at the same way again?